Welcome, everyone. Today, we're diving into one of the most pivotal principles in physics, the conservation of energy. This principle helps us understand how energy moves and changes form, influencing everything from the operation of simple machines to the dynamics of the cosmos. Let's unravel the mysteries of energy together. The law of conservation of energy states a fundamental truth: energy cannot be created or destroyed. It's a constant traveler, changing forms but never fading into nothingness. This principle underpins much of our understanding of the physical world, guiding us through the complexities of energy transformations. Consider a closed system, a sealed-off stage where the drama of energy plays out. Here, the total energy remains a constant figure, unchanging over time. Energy within this system may morph from kinetic to potential, from electrical to thermal, yet its total quantity remains untouched, a testament to the steadfastness of energy conservation. To visualize the flow and transformation of energy, we turn to the Sankey diagram. This powerful tool represents energy transfers, with the width of each arrow mirroring the amount of energy moving to each store. It's a visual symphony of energy efficiency, showing us at a glance where energy is allocated, used, and lost. At the heart of energy conservation lies a simple, yet profound equation. Total energy input equals useful energy output plus wasted energy. Total energy input equals useful energy output plus wasted energy. This equation balances the scales of energy input and output, highlighting the inevitable presence of energy that is transformed but not used for work. It's a fundamental formula that quantifies the essence of energy conservation. The law of conservation of energy is not just theoretical, it applies to real-world processes, such as the burning of petrol in a car engine. Consider this: for every 120 joules of chemical energy in petrol, only 50 joules propel the car forward as kinetic energy. The remaining 70 joules escape as heat, an energy loss to the environment. This example illustrates the practical implications of energy conservation and efficiency in everyday technology. Let's solve an exam question. A pendulum bob swings along the path WXYZ and back again. Resistive forces can be ignored. Which statement describes the total energy of the bob? Option A, it has a maximum value at X. Option B, it has a maximum value at Y. Option C, it has a maximum value at Z. Option D, it has the same value at W, X, Y, and Z. Let's paint the picture. Consider a pendulum bob that swings from point W, through X and Y, to Z, and back again, without any resistive forces. At the highest points W and Z, the pendulum's energy is all potential. At the lowest point X, the energy is all kinetic as the bob swings at its fastest speed. But here's the key: if there are no resistive forces, the pendulum's total energy does not change throughout its journey. It doesn't matter if it's at W, X, Y, or Z, the total energy remains constant, a fundamental principle known as the conservation of energy. So, option D is correct. The pendulum has the same total energy value at W, X, Y, and Z. Remember, the pendulum's energy isn't disappearing, it's just changing from potential to kinetic and back, perfectly conserved. And that's a quick insight into the energy of a pendulum. Energy conservation is a cornerstone of physics and is vividly demonstrated by the simple pendulum's motion. Thank you for tuning in, and keep pondering the physics in motion around you. Let's look at the exam question about energy efficiency. The diagram represents the energy transfers for a device. The device is 50% efficient. Which equation is correct? Option A, input energy equals useful output energy divided by 2. Option B, useful output energy equals wasted output energy divided by 2. Option C, wasted output energy equals useful output energy. Option D, wasted output energy equals useful output energy divided by 2. Let's have quick explanation. We will clarify the concept of energy efficiency using a straightforward example. We have a device that is 50% efficient, meaning that it converts half of the input energy into useful work, while the other half is inevitably lost as wasted energy. The correct equation to represent this situation is option C, wasted output energy equals useful output energy. This is because, at 50% efficiency, the amount of energy wasted is equal to the amount of energy that is used effectively. In numerical terms, if 100 units of energy are input into the device, 50 units are used for useful work, and 50 units are wasted, they are equal. Remember, the efficiency of a device is a measure of how well it converts input energy into useful output, and understanding this helps us gauge the effectiveness and environmental impact of the device. Look at an exam question talking about work done against resistive forces. A stone of mass m is held at rest in water. The stone is released and falls vertically a distance h. The stone reaches a speed v. Some of the original energy of the stone is transferred to the water. As it falls, resistive forces cause the temperature of the water and stone to increase. Which expression gives the work done against the resistive forces? Option A, 1 over 2 mv square. Option B, mgh minus 1 over 2 mv square. Option C, mgh. Option D, mgh plus 1 over 2 mv square. Take some time to correct option. Work done against resistive forces can be considered the energy that is not converted into kinetic energy. Initially, the stone has gravitational potential energy mgh. Upon reaching speed v, it has kinetic energy 1 over 2 mv square. The difference between these energies is the work done against resistive forces. The correct expression for the work done against resistive forces is option B, mgh minus 1 over 2 mv square.
Here you can see that there is a simulation that is related with the energy conservation. Let's open this. You can see here there is a wire that is moving on this path, and here there is a chart which is showing the energy, means that EP is the potential energy and EK is the kinetic energy. EF is the energy that is lost due to friction, but here we are actually ignoring the friction. Then all of the potential energy is converted into the kinetic energy. First of all, see the position of this Y. When he is at maximum height, all of the energy is basically the potential energy. But when it's going towards the ground, potential energy is converted into the kinetic energy, but the total energy remains the constant, which is 100%. Now see the position of this Y, it's at the ground. All of the energy is kinetic energy. That's why the red bar is completely until 100%. When he is moving towards the height, then there is the loss of kinetic energy and potential energy is increasing. So that's why there is a transfer from kinetic energy into potential energy. When he reaches at some height, there is a sum of both potential energy and kinetic energy. But at the maximum height, all of the energy would be the potential energy. Kinetic energy at the maximum height would be zero. You can observe this by yourself as well. Now let's consider I am also counting the friction, then what will happen? First of all, I stop this. Count the friction. Now I will start it. See that when the Y starts from the maximum height, at this point there is total potential energy. There is no other form of energy. When he is moving towards the ground, there is some transfer of the energy from potential energy into kinetic energy. But when again he tries to go at the maximum height, he cannot reach at the maximum height. It is because of the reason here we consider the friction. Frictional actually reduces the height of that object. So you can see here he cannot attain the maximum height and return back. I can simply say that when you count the friction, you cannot get the potential energy 100% even at the maximum height because the Y is unable to reach at the maximum height. But the total energy, you can see here, it remains the constant. No, there is the extra bar which showing the energy that is lost due to the friction. So in this way, the total energy is conserved, which is shown by the black bar. But the energy is transferred into different forms. Next is again the simulation that is related with the energy conservation. Let's open this also. First of all, I open the intro. Here you can see that there is a girl that I suppose that I bring it at the maximum height. Then which transfer of the energy take place? First of all, I place here the pie chart. You can see the pie chart. Here the transfer of the energy take place. Here on the side you can see the blue is showing the potential energy, the green is showing the kinetic energy, and the red is showing the thermal energy. Here when she moves, there is only the transfer of the energy from kinetic to potential and potential to kinetic. You can also check the speed. At the maximum height, her speed is 0. When she goes towards the ground, then the speed is maximum. You can check here as well the conversion of kinetic energy and potential energy. Here is also the bar chart. Check this bar chart. The total energy is conserved even if it's transferred from kinetic energy into potential energy and potential energy into kinetic energy. Let's consider the other path. This one. At the maximum height, there is only the potential energy. When this girl comes at the ground, here all of the energy is kinetic, but the total energy remains the same. In the last one case, I again place her here at the maximum height. See, the potential energy decreases and kinetic energy increases. There is a conversion of both of these energy, but the total energy remains same. You can also check the other as well. Here in the second one, they count the friction. When there is a friction, then what will happen? I suppose that here I place the bar chart. No, first of all, she is at maximum height. Here, as there is a friction, some amount of the energy is lost as a thermal energy. So let's start this. She is moving downward. When she reaches at the bottom, she has kinetic energy. No, she cannot even reach at the maximum height because here is also the thermal energy. Due to the friction, some energy is lost into the thermal energy. But the total energy always remains constant. There is no change in the total energy. You can practice this as well.